All right, like I said, we are starting my favorite material today, logarithms. Well, some of my favorite material. I really love trig too, but logarithms. And we start logarithms with log base 10. Anybody, anybody know why we would start with log base 10 specifically?
Because that makes X 100. It's a pretty nice number.
So,
X 100.
so we got a couple ideas. You want to know the real reason why we start with log base 10? Because our number system is base 10. The number system that we use every single day is base 10. That's why we call the places of our numbers ones, tens, hundreds, thousands. Any computer people understand it's actually binary, but base 10, basically. That's why they're called tenths, hundreds, thousands, things like that. Each place is actually a power of 10. So our entire number system is base 10. Okay, here is the thing that unlocks logarithms, I think. And it's what unlocked it for me. Of course, I'll give you a little bit more explanation to show you why. But here you go. Here's the dirty secret. Anything in math that can be done can be undone. There it is. Mic drop. Okay? Logarithms have a job. A logarithm's job is to cancel something else. Let me give you an example of what I'm talking about. In elementary school, the first thing we teach you how to do is add, correct? That's the first operation you learn in mathematics. What's the second operation you learn? Subtraction. You know why? Because it undoes the addition you just learned. Somewhere along the line, you learn multiplication. Not very long after, you learn division. Because guess what? It undoes the multiplication. You see what I'm getting at is these things are called inverse operations. We teach you how to raise things to powers, then we teach you how to cancel them with radicals. Inverse operations. Logarithm is an inverse operation. And the sooner you just believe that, the sooner you'll completely understand them. So what makes them so abstract for students is, well, one, it's not a symbol. It's what appears to be a word, right? Where every other thing that you do in math is represented by a symbol, logarithms are represented by a word. And that's what makes them so abstract. What makes them hard for students to understand? And when I say understand, I don't mean get the right answer, because lots of people can get right answers, but it doesn't mean you understood why the answer worked. Now you could quote, well, I used this rule and this rule, but then I say, but why does the rule work? You probably don't know. Why not? Because your teacher didn't show you. Why not? Because they don't know either. Okay? Now, I'm not pooping on math teachers. I'm just saying there's a lot of math teachers who don't understand the logarithm. They can teach you to get right answers. That doesn't mean they understand. It doesn't mean you understand. That just means you got a right answer. Woo. Okay? I'm going to teach you to understand them, and then I think most of you will never, ever hear the word log and feel pain in your guts again. Okay. Not an inverse to exponents, but kind of. We'll get there. We'll get there. So everything in math that can be done can be undone. If we can raise bases to unknown exponents, 2 to the x, 3 to the x, if I can raise a base to an unknown exponent, there must be an algebraic operation that undoes that. That is what logarithms do. Logarithms don't cancel an exponent. Logarithms cancel the base. A logarithm's job is to cancel the exponential base and leave behind the exponent. Still abstract because a word. When we are finished mastering logarithms, I will show you the symbol that I came up with for logarithms instead of writing log. And I don't know why mathematicians never did it. I don't know why, but I'll show you. Okay, so let's just go through the way IB wants you to learn these things. Oh, I forgot to mention this inverse property right here. It says if f of x is 10 to the x, then f inverse of x, its inverse must be log base 10 of x. Notice that this is base 10 and this is base 10. You see the bases match, and that's what makes them inverses of one another. Base 10 raised to the x is the inverse of log base 10 of x. And don't worry, like I said, we'll get to y and things like that. Okay, all positive numbers can be written in the form of 10 raised to some power as long as you're using logarithms in base 10. The logarithm in base 10 is of a positive number, is the power of 10 that must be raised, is the power that 10 must be raised to in order to obtain that number. What a weird thing to say, but here we go. The number a, like 2, let's just say 2, is equal to 10 raised to the log of 2. So 10 raised to the log of 2 is equal to 2. And by the same logic, log of 10 raised to the x is x. What I'm getting at here is that exponential, and by the way, notice that this log and this log, whoops, I underlined this log and this log. Notice that there's no base written. It's called the common log. Log of a is log base 10 of a. It's called the common log. And the reason why it's the common log is because our number system is base 10, so it's the most commonly used logarithm. So you don't see a base, it's 10. It's like square root. You know how it doesn't have the index, the little 2 written on it, but it is technically there? It's the same idea. What we're getting at here is that, gimme, in either order, log base 10 and exponential base 10 cancel each other out. Log base 10 and exponential base 10 cancel each other out. In all actuality, log base b of b to anything is anything, because log base b will cancel exponential base b. They're inverse operations. As long as the bases match, they're inverse operations. Log base b cancels exponential base b, and that's why this works like that. And in this, the other order is the same. Let's see. B raised to the log base b of x still equals x. Again, log base b and exponential base b cancel each other in either order because they are inverse operations. Just like addition and subtraction will cancel each other in either order, as long as they're the same number, right? So what I'm saying here, as long as they're the same base, they'll cancel each other. Yeah, I know. Logarithms are not magic. Logarithms are algebra. They are an operation. They are an operation. That's why you can't just say, oh, doesn't log equal? No, stop immediately. It's like saying, doesn't plus sign equal? No. You see, symbols don't have value in mathematics. They're operations. A logarithm is an operation. That's why you can't just say, oh, log equals some number, because square root bar does not equal some number. Operations don't have value. So it says, without a calculator, figure out what log of 100 is. And I go, well, fine. I just taught you, and this is not the way IB wanted me to teach you, but screw them. I just taught you that if you're missing the base, it's common log, right? Which means it's log base 10. So I'm asking you to tell me what is log base 10 of 100, and rather than just saying the answer, we're going to show why the answer is true. Because why something is true is much more powerful than here's the answer. Log base 10 has a job. Log base 10's job, cancel exponential base 10. So the question becomes, is 100 a number that can be written in base 10? Of course it is. It's 10 to the second power. So this is log base 10 of, and I'm going to use parentheses for the argument. By the way, that's what this position is called. The thing the thing that you're taking the log of is called the argument. See, log base 10 has a job. Its job is cancel exponential base 10. Here, log base 10 gets to do its job. And you're left with 2. If log base 10 couldn't do its job, then log base 10 would still be hanging around. Kind of like I ask you to, what is the square root of 3? And you say, it's the square root of 3. You see, you have to keep the symbol. Why? Because the symbol couldn't do its job. It couldn't take the square root of 3 pretty. Logarithms act the same way. If it can't do its job on a number, then the logarithm sticks around. If it can do its job, which means cancel something, it goes away. Aaron. Well, the 100 didn't cancel the 10. The log base 10 canceled the exponential base 10. Because instead of writing it as 100, I wrote it as a number that is base 10. I wrote it as 10 squared. This way, the log base 10 could do its job. And the second one. Again, I am going to write log base 10. Log base 10, I don't have to, but I'm going to. And, okay, so this is weird, right? This is strange. I need to write the 4th root of 10 as a power of 10. This way, log base 10 could do its job. So what is that exponent on that 10? 1/4, not negative 1/4. Now the log base 10 can do its job of canceling exponential base 10, leaving me with 1/4. Inverse operations. I remember the moment I realized, oh my gosh, it's an operation. It cancels another operation. Holy crap. Why did nobody ever say this to me? I just got goosebumps thinking about it. You guys think I'm crazy, but math does that to me sometimes. Like, wow, a realization, an understanding. That light bulb, powerful. How many operations are there? I'd say infinite, to be honest with you. They never stop. How many operations do I know? I don't know. How many operations do I understand? They stop somewhere around the calculus part. It's like, after that, math just gets a little weird. Okay, this one says to use your calculator to write the following numbers in the form 10 raised to some x, where x is correct to 4 decimal places. Let me show you what we're talking about. I'm trying to say that 8 is 10 raised to some number, like this. And I go, okay, the only way this is going to work out is if the exponential base 10 can cancel a logarithm, a log base 10. So we go, okay, 8 is 10, exponential base 10, raised to the log base 10 of 8. You see, because the exponential base 10 and the log base 10 would cancel each other out, leaving a statement that just says 8 equals 8. What we've been asked to do is to figure out what is log base 10 of 8. That's what that says to do. And it says to take it to 4 decimal places. So 8 is 10 raised to the, and I'm going to grab handy dandy calculator because you can't evaluate logarithms by hand if they are irrational. And I'm literally going to just type log of 8. I don't need to say base 10 because it's the common log. On everybody's calculator, there's a button that just says log that assumes base 10. So I'm going to say, what is log of 8? And to 4 decimals, it should be 0.9031. 0.9031. And yes, if you raise 10 to that power, you will get something dangerously close to 8. Now, Kirill has already heard all of this stuff, so he didn't miss anything.
The log word.
It's the log word. Before I move on to part B, I just need to make sure that everybody understands what we just did. we used an exponential base 10 to cancel a log base 10 that allows us to write any number as 10 raised to some power. Part B. Again, you're asking yourself, what power would I have to raise 10 to get 800? And I go, well, it's got to be a pretty number, 800. It can't be, the 800 is not irrational. That means that 10 must have been canceling something, leaving behind an 800. And the only thing exponential base 10 can cancel is a log base 10. I'm going to stop writing base 10, if you're okay with that. No one ever writes base 10. You see right there, the base 10 and the exponential base 10 and the log base 10 would have canceled out, and you would have had 800 equals 800. So I just need to know, what is log of 800? I bet you without touching this calculator, and you see I'm holding no notes, right? I bet you it's 2.9031. Right? But how'd I do that? Because 800 is 8 times 10 squared. I just put the exponent of 2 in front of 0.9031.
Oh, I see some. Yeah. I see.
Did you have to understand that right there? No. But if you did, awesome. I'm going to squeeze C in here. 0.08, 10 raised to some power. I go, okay, well, I know it had to be log base 10 because that's the only thing exponential base 10 could cancel. So it must have been log base 10 of 0.08. And without a I'm holding a calculator, but just see I'm not working it, not using it. That's what I meant to say, not using it. I bet you it's 0.9031 plus -2, or 0.9031 minus 2. In fact, I will do 0.9031 minus 2. I said minus 2. I got the exponent of -1.0969. Is that what log of 0.08 is? Cool. How about that? Math works. Yes, it does. 10 raised to the... I couldn't get that negative decimal in my mind, but I can tell you why it was true. 0.969.
Why was it 969 instead of?
Because notice that this number is 8 raised to the negative 100. So what it did was it took 0.9031 and it subtracted, because 10 raised to the -2. That's why.
Oh, I see.
Yeah. Adding numbers to decimals is easier than subtracting. But that's why that works. So I can write any number as base 10. Guess what? You could write any number as any base you want. Does not matter. I could say 7 is a power of 2 very, very easily. What is it? 7 is 2 raised to the log base 2 of 7. There it is. Now, I don't know what log base 2 of 7 equals, but that's how you would say that 7 is a base 2 number with logarithms. Their job is to cancel exponential bases and vice versa. All operations have an inverse. I've never come across a mathematical operation that cannot be undone. Everything can be undone. Can I move to the back, I'm assuming? Is it the back now, or is it more? No, I meant like there's nothing lower on this side? Awesome. Let's flip it over. I love logarithms, yes I do. Come on, next. Catch up with me, active panel. Thank you. Good gravy. It says use your calculator to find log of 2. Okay, you literally type log 2. I don't know what log of 2 is. I don't have my notes in my hand. Hold on, wait. Will you give me to 3 sig figs? So 0.3 1.301. Okay. I knew that that number had to be less than 1. I did know that. And I knew that number wasn't negative. Let me explain to you how I knew that, because it's powerful to understand this. How did I know the answer was less than 1? Because 10 to the 1 is 10. And since 2 is smaller than 10, I knew I had a number less than 1. But I knew it had to be positive because 10 to the negative 1 would have been 0.1. It would have been way too small. So because this was still an integer value, I knew that I was dealing with a positive number. Not to mention, 10 to the 0 is 1. So since this is bigger than 1, I knew the answer was bigger than 0. This is just power. So log of 20, without a calculator, I could tell you what log of 20 is. Because log of 20, because 20 is 10 times 2, how many powers of 10 have I, quote unquote, added? 1. So the answer had better be 1.301, because now there was an extra power of 10. Not to mention, 10 to the 1 is 10, and 10 to the 2 is 100, and the number 20 is nowhere near 100, but it is bigger than 10. You knew your answer had to be between 1 and 2, but closer to 1. This is how you estimate logarithms. So cool. God, I'm a nerd. Okay, so part B says, explain why this was true. Explain why it's true. And I go, okay, well, here's why. See, how do I do this without cheating and using future knowledge? Log of 20, let me use parentheses, is the same thing as saying log of 2 times 10. Right? Is that how I just want to make sure that's how I explained it in the notes. Oh, I'm way past that. The way I'm about to do it is going to break some rules. Ah, there it is. Okay, that's what it was. I'll be okay. What we can do is we can say, now let's go to the argument. I can say that that 2 is actually a power of 10, like we did on the front. I can say that that 2 is 10 raised to the log of 2 times 10 raised to the 1. Are you comfortable with me making that statement? I need to know. We were comfortable with me turning 2 into 10 raised to the log of 2? Why'd I do that? Because now the two numbers in the argument are both base 10. And when you multiply two numbers with the same base, what do you do with the exponents? Come on, guys. When you multiply two numbers with the same base, what do you do with the exponents? You add them. So this says log of 10 raised to the log of 2 plus 1. And now log base 10 gets to do its job. Cancel exponential base 10. Do you guys remember that rule from Algebra 2 that says, and it's okay if you don't because we're going to reteach it, quote unquote, but do you remember the rule from Algebra 2 that said that when there's a multiplication in the argument, it's actually the addition of two logarithms? You guys vaguely remember something like that? This is why it's true. Rather than tell you it's true and ask you to memorize it, I can demonstrate it very, very easily. This is why. Yes, sir?
So before you got that second example, you wrote it as 10 log.
Mm-hmm.
I originally thought about it as like similar to, I guess, distributing the property.
Kinda.
Or is that just something that applies to you?
So what you were thinking of is you actually were kind of using prior knowledge of that whole when there's a multiplication in the argument thing. but I was trying to do it without using that rule because we don't know. For so far, you've only been told it's true. You haven't been shown why it's true. And this isn't even showing you why it's true. It's showing you that this is why it works, but that's just a demonstration. It's not a proof. You prove math with no numbers. You prove it using only letters. So it's not that it was I know you're thinking about it as a distributive kind of thing, but then the question when you say things like that, it's like, then why did the multiplication become an addition? And people get confused. So instead I go, well, we all understand that when we multiply two numbers at the same base, we have their exponents. So that's why we take this road, because it uses a prior skill. All right, so these down here, is this it? Is this it for the notes? Is these right here?
Yeah.
Cool. So allow me to show you how to solve for the argument of a logarithm. Every operation that can be done in mathematics can be undone. I'm trying to get x by itself. That means I'm attempting to cancel a logarithm. This is log base 10. So the question becomes, what is the inverse operation of log base 10? What would log base 10 cancel? Exponential base 10. So what would cancel log base 10? Exponential base 10. Inverse operations cancel each other in either order. From now on, if I say what would cancel log base b, you say exponential base b. If I say what would cancel exponential base b, you say log base b. If I say exponential, you say log. If I say log, you say exponential, and you just make sure the bases match. Because that's what logs do. So there must be an inverse operation of log base 10. It is exponential base 10. So I'm going to use quotations here. This is not a true math operation, but this is how it works. You exponential base 10 both sides. What you do is you pretend that both of the sides of this equal sign were actually exponents. And you have done this before. You just didn't know it. When we were solving exponential equations by hand, the process that I told you was make the exponential bases match. And once they match, you set the exponents equal to each other, right? I'm doing that in reverse order. The only reason, remember when I was like, it feels like there must be a reason why I'm allowed to do that, and then I didn't say it and I moved on? It's logarithms. I didn't just forget about the exponential bases. What I did but didn't show was I canceled them with a log operation on both sides. You can't cheat math. It had to be algebra. So I haven't cheated. What I've done is I've said, what if both of those things were already exponents and the base was 10? Why did I choose 10? Because that would allow me to cancel that. That's why I did it. So what you get is that x equals 10 to the third. Oh, x equals 1,000. I know, doesn't it? Logarithms seem so magic and abstract in Algebra 2. Unless you were my Algebra 2 student. Yeah.
I don't know, I just felt like I wanted to say it. I just kind of realized when you were doing that. It's also saying with the log, what power do I have to put the base to equal that x?
Yeah.
So it's saying 3.
Yeah.
So it's like an understanding thing.
You know that trick in Algebra 2 where they're like, write this number in log form, write this number in exponential form, and they show you little cutesy tricks, but you don't know why it's working? This is why. You can't see the face. This is why. I don't teach those tricks to my Algebra 2 students. I teach them first the algebra of why it works, and they go, oh, and by the way, this is what it looks like, shortcut little arrow deal. But you know why it's working. They're not magic. They're algebra.
Did you show them your own symbol yet?
Who?
You.
Pre-calc kids?
No, us.
No, not yet. I'm going to wait until closer to the end of the chapter. But the symbol makes sense, doesn't it?
forgot it. So.
Oh, this guy, he forgot. Okay. So log base 10 of x is approximately negative 0.271. If you would like to know what x is, you have to cancel the exponential base 10. Hey class, what cancels exponential base 10? Crap, I said it backwards. Dang it. Oh, I effed up my own script. I got too excited about logarithms. What I meant to say was, hey class, what cancels logarithm base 10? These guys, you're supposed to say exponential base 10. So you exponential base 10 both sides. Killing me. That's okay. When I do it with algebra 2, I make them tell me a script. I go, now we're going to try again. You all didn't say it right. And they are good at logarithms. So on the left side, these guys go bye-bye. And we get that x is approximately 10 raised to the negative 0.271. And I'll be darned if I know what that number is. So I would grab handy-dandy calculator or walk over to my notes. 0.536. Just make sure that you can get that number. We good? All right, everybody's able to get that? Fantastic. Yay, we have scratched the surface of logarithms.